Hello everyone, I'm Dongwei. Today I will present our work on ensuring social-optimal and revenue adequacy. We design mechanisms for low-carbon energy resources investment in deregulated electricity market. Nowadays, driven by the zero-carbon target, the low-carbon energy resources are increasing rapidly in the recent years. The first figure shows the global solar PV capacity in the last decade, which is from about 40 to 800 gigawatts. The second figure shows the US historical and planned capacity of large-scale battery storage, which expected a significantly increase after the year 2020. A lot of countries and areas have established the targets of zero carbon. For example, in California, they established the goal of getting to zero carbon electricity by the year 2045. In the future, it is expected there will be more and more low carbon energy resources investment in the market. In practice, there can be different modes of market to plan the low carbon energy resources. In this work, we focus on the deregulated electricity market, which is the practice of some countries like the US. In the deregulated market, the investors can decide the capacity investment and output operation in the market by themselves. They can try to maximize their profit in the market. In contrast, we also consider a centralized market as a benchmark. Here, the system operator will decide everything, including the capacity and the output operation in the market. We regard it as the social-optimal benchmark for the deregulated market. Note that in deregulated markets, the investors are profit-seeking. However, with the increasing capacity of low-carbon energy resources, those investors may face the diminishing revenues in the market. For example, the renewable energy usually has very low marginal cost, which is expected to drive down the wholesale market price and reduce the revenues for the investors. Then, facing the diminishing and limited revenues in the market, there will be natural competition between those profit-seeking investors. They will compete in the investment and operation of those renewable energy and energy storage. This can lead to the strategic behaviors of those profit-seeking investors. For example, they may withhold some capacity in the market to uphold the electricity market price. So it will be a problem how to ensure the revenue adequacy to the investors due to the reduced market price and the revenues. And there is also a problem of the strategic behaviors which may deviate from the social optimum. So in this work, we try to answer two key questions. The first is that how can we design mechanisms for those competing investors in the deregulated market so that we can guide their behaviors towards social optimum? The second is that considering the decreasing market prices due to the low carbon energy resources, how can we ensure the adequate revenues for the investors? Next, I will introduce our system model. First, I will introduce the centralized market as a social optimal benchmark. Here, the system operator will plan all the resources in the market. The objective is to minimize the system cost, including the investment and operations. For the decision variables, they include the invested capacity of all the resources and operations of those resources. For the operations, they include the output of the new invested low-carbon energy resources, the output of existing fossil resources, and the potential lost load in the system. Then for the constraints, we have the demand balance. There is the new output from the low-carbon energy resources plus the output from fossil resources, which is equal to the net demand minus the system lost load. We also have the capacity bound for all the resources. Now I will introduce our deregulated market model, where a set of investors will compete with each other to maximize their own profits. There can be different investors, including solar energy, wind, and energy storage. They will decide the invested capacity and their energy output on the market by themselves. Note that all the investors' decisions and profits are coupled with each other. That is because their investment and operation decisions will impact the market price and then further impact their market revenues. To model the coupled and strategic behaviors of those investors, we utilize the game theory model. In the game theory model, the profit of each investor is the market revenue minus the capital cost minus the operating cost. Here the market revenue is the output times the market price. Note that the market price is determined by all the investors' investment and operation decisions. This is a key component of our model, which leads to the coupled strategies of all the investors. In this game theory model, we are interested in finding out the Nash equilibrium of the investment and operation of all the investors. Nash equilibrium is a stable state that nobody will deviate from his current strategies. It means that at the Nash equilibrium, every investor is making the investment and operation decisions, which is the best response given other investors' decisions. Now the question is, how do we model the market price in the deregulated market? There are some existing market mechanisms with the scarce price, which is commonly used in the US market. To illustrate, we show a simple supply curve. Renewable energy is first dispatched, and then fossil energy, and then lost load. If there is some lost load, it will lead to the scarce price in the market. In Texas, the scarce price is set about $9,000 per megawatt hour. You can see that the scarce price can be very high, which is not beneficial to consumers. This is often criticized. However, if you give some price cap on the scarce price, it may also lead to the revenue loss for the investors. In this work, we prove that under perfect competition assumption, the scarce price can achieve the social optimal under some conditions. However, considering the imperfect competition, which is more practical, the market power can be easily abused due to the extremely high scarce prices. In this work, we try to design some new market mechanisms to get rid of the scarce price. As illustrated in this figure, when there is lost load, we will not consider the extremely high prices. Instead, the market price is always bounded by the marginal cost of some fossil energy resources. However, there are some challenges regarding the mechanism design without the scarce prices. The first is that how can we reflect the cost of the lost load without the scarce price? The second is, under imperfect competition, can we avoid the market power abuse and guide the investors' decisions to the social optimal? The last is that without the scarce price, how can we ensure the revenue adequacy for the investors? Next, we will introduce the mechanisms to tackle the three challenges respectively. First, to reflect the cost of the lost load in the market, we design a penalty payment for the lost load in the investor's decisions. Each investor needs to decide an additional item of the lost load, which is the decision variable. The system operator will aggregate all the investors' decisions to ensure the demand and supply balance. Accordingly, each investor needs to pay a penalty based on the item of the lost load. This penalty is related to the cost of the lost load. Based on the penalty payment, we can establish the equivalence of the game theory model and the social-optimal benchmark. With the linear supply curve without scarce price and the penalty payment for the lost load, we can prove that under the infinite number of the investors, the Nash equilibrium of the investment and operation of all the resources is equivalent to the social-optimal benchmark. However, this result is under the infinite number of the investors. In practice, there are always finite numbers of the investors. The finite number of investors always leads to the imperfect competition in the market. The investors will tend to withhold the capacity in the market and uphold the market price to increase the revenues. So in this work, we further design a supply incentive to the investors. We design an additional incentive item based on the quadratic outputs of each investor, which is shown here. We can prove that together with the supply incentive, the Nash equilibrium will be equivalent to the social-optimal benchmark, even under the finite number of the investors. Now we come to our last challenge to ensure the revenue adequacy to the investors in the market. We can see that without the scarce price, when there are more and more low-carbon energy resources and more retirement of the conventional fossil resources, the market price will be reduced in our mechanism. So it's a problem that the investors can get negative profits at the Nash equilibrium. In this simulation results, we show the profit of the storage, solar, and wind investors with the retirement ratio of the conventional fossil resources. You can see that the profit can be negative when we increase the retirement of the conventional fossil resources. To solve this problem, we try to uplift the energy price for the investors. The idea is to increase the market price by a regulated value delta pi as the base rate. We uplift the supply curve by delta pi as illustrated in this figure. Note that the delta pi can be set differently for the different hours and different days, which can be very flexible. We can show that such energy price uplift is effective because there always exists delta pi that achieves non-negative profits for the investors. However, by adding such energy uplift, it will make the Nash equilibrium deviate from the social optimal because it will incentivize the investors to invest in more resources. However, we can show that such deviation will be reduced with the increasing integrations of the renewable energy in the market. In the simulation results, I will use the real data in California market to construct the supply curve. I examine the recent 3 years data, price data, and the net demand data. We plot the price with respect to the net demand for each month, and the different colors represent different years. Overall, the relationship can approximate a linear function where we use the linear regression to construct the supply curve. The supply curve can represent the market price function as well as the system marginal cost. I will not go into more detail about this part. In the simulation results, we show the Nash equilibrium results under the mechanisms of the penalty payment, supply incentive, and energy price uplift. We consider 3 investors compete: wind, solar, and storage. The first figure shows the system cost with the energy price uplift. The different colors represent the different retirement ratio of the conventional fossil resources. We can see that when the energy price uplift is 0, the system cost is just equivalent to the social optimal. However, if we increase the energy price uplift, the system cost will deviate from the social optimal. If we increase the retirement ratio of the conventional resources, for example, 90% in the blue curve, the system cost will be always close to the social optimum. The second figure shows the profit and average market price with the energy price uplift. We can see that the energy price uplift can lead to the positive profits for the investors. At the same time, it will not increase the market price very significantly. This concludes my presentation. Thank you all. Welcome any questions.